Today from Marine Engineering Base, we are going to discuss about shipboard electrical power generation. For easy discussion, there are few learning objectives that we can discuss. First one, basic layout of ship's electrical system. Then basics of some magnetic induction and EMF. Bus bar and its connected loads, resistive loads, inductive loads and capacitive loads. How the system manage with active power and reactive power. Main principles behind power generation. Governor and AVR response against kilowatt and kVAR reactive load changes. As a start, here we can see small diagram. So ship power management system. There are two generators connected to the main switchboard via a circuit breaker. Thereafter, from the main switchboard, we are taking the electrical loads. So all the electrical loads such as pumps, motors and the lightings are taking the load power from the main switchboard. In modern days, for propulsion purpose that we use the power generated by the generators, as well as auxiliary thrusters we are using with the electrical power supply. Here we have to discuss few electromagnetic principles before we touching the main concept behind the ship's power generation. There are a few diagrams in this clip. You can see there's a copper coil, conductive coil, and also a magnet. There's a principle according to Faraday's and the Lenz law. You can refer separately if you want more detail, but here in simple, if you move a magnetic field which cuts the copper coil, then there will be an induced EMF in the coil. So there will be a voltage appear in this galvanometer. In opposite direction, if there's a coil and if you apply a current through the coil, then there will be a magnetic field induced around the coil. These two principles are very important. The first one, whenever the copper coil is subjected to varying magnetic field, there will be an induced EMF. The same way, in the opposite, when the copper coil is subjected to a current flow, there will be an induced magnetic field around the copper coil. And this induced EMF, if it is V, there's an equation that the amount of this EMF is depend on total flux density and also the flux cutting rate d phi by dt, and here's a constant that is the number of turns of the coil. So we can summarize this as follows. When a copper conductor, a coil, under the influence of changing magnetic field, then there will be an induced EMF generated within coil. In first case, if the coils moves with relative to static magnetic field, that means as per this figure, if the coils moves when the magnet is stationary, there will be an induced EMF within this coil. If the magnetic field varies whilst the coil remains steady, if the magnetic field, now here in this case, the magnetic field, if you can move the magnet, and then there will be an induced EMF also. The second theory that we discuss, when a current flows through a copper coil, then there will be an induced magnetic field around the coil. Suppose if you can supply some current here, then there will be a induced magnetic field around this coil. If the supply is DC supply, then the magnetic field have a permanent, it acts as a permanent magnet. Even though it is an electromagnet, then it has a fixed polarity. If the supply is AC, then the magnetic field polarity will also change with respect to the supply voltage polarity. This is the main diagram that I'm going to discuss today, the shipboard power generation. Surrounding we can see some components, physical appearance of these components. Here is the diesel prime mover and here is the alternator, we can see it here, and the physical appearance of AVR, main switchboard and the alternator rotor assembly appearance. Here are some loads, resistive load, inductive load. This is a strip view of a motor, electrical induction motor, and capacitive load. This is a starter of a fluorescent lamp. So this main diagram, it consists of a generator with a prime mover and an alternator, and this alternator is supplying to the bus bar through a air circuit breaker, and from this bus bar there are three kind of loads theoretically we can discuss: resistive loads, inductive loads, and capacitive loads. In this diagram here in this area, I've shown one pole of this alternator rotor. It consists north and south, and the flux distribution that we will discuss in future. And here in this corner we can see the internal schematic diagram representing the cross-sectional view of the alternator. As we all know, prime mover is a diesel engine which rotates by using the energy of fuel. The speed of the prime mover depends on the supply of fuel. So to maintain a constant speed, we want to regulate the fuel. So that purpose we are using a governor. The governor sends the prime mover output RPM or the speed. As per that, it regulates fuels and control the prime mover speed. Suppose if you are riding a motorbike, if you want to run it through a flat road, then you have to regulate your accelerator. In that case, you are the governor. And if you reaching a mountain, then to maintain the same speed, then you have to increase the accelerator to increase the fuel. In the same scenario, if due to some reason, if there's a retarding torque that to lower the speed, then the governor will sense this lowering of speed and then increase the fuel to maintain the speed constant. This part we call it alternator. For easy understanding, now we are going to discuss the basic construction of an alternator. In this diagram, we can see basic cross-sectional view of brushless generator. So here the shaft is connected to the prime mover, this end, and then bearings are there and a fan for cooling purpose. An alternator consists of two main parts. As we can see, it is a main rotor and main stator, and the exciter stator and the exciter rotor. So main rotor and the exciter rotor are in the same shaft, which has the same speed as your prime mover does. And this main rotor is enclosed by a main stator copper winding. Same way, the exciter stator also surrounded the stator exciter rotor. And we can see a device called AVR, automatic voltage regulator, is monitoring the main stator voltage, and depending on the set point feed by the operator, it will increase or decrease the excitation voltage of the exciter. In returns, the main rotor magnetic field will be vary to maintain the set value of the stator voltage output. Okay, now we can see here, as we discussed earlier, this is the main rotor, so we can see the main rotor like that, the fan, and this is the exciter rotor, so we can see exciter rotor, and the rectifier bank is there. We will discuss what is the purpose of there. So the physical view is like that. So this is the schematic diagram. So generator rotor is there, this is the generator rotor, this part, and the rotating rectifier bank is there, and the exciter rotor is there. This is the exciter rotor, it part is here, exciter stator here, and this is main stator winding. Okay, this enlarged view, then we can easily discuss what is happening in alternator. We can see this cross-sectional view. This is the main rotor, north south, one pole we are going to discuss, and this is the excitation voltage. Here we show with the DC supply, variable DC supply, and this A, B, C are the stator winding coils. So stator winding coils are these blue coils, this rotor is this purple coil, and excitation coil is more or less this part is this excitation voltage, and the diode bridge is conversion from AC to DC supply. Now we can see the prime mover is rotating at a RPM that we set to run. As the prime mover rotates, the whole rotor is rotating. That means the exciter rotor and the main rotor both are rotating the same RPM. Let's say it's 900 RPM in general case. Now we can see, we saw that in the previous diagram there are copper coil in main rotor field and also copper coil in exciter field rotor, and also another set of coils in stator winding as well as in exciter stator winding. Suppose if we can give some DC voltage here, then there will be current flow in this coil, exciter field stator, and if it is, as it is a DC supply, in magnetic theory that we have discussed, if we supply a DC voltage, there will be a permanent magnet. Here let's say north south, there will be a permanent magnet. But in this permanent magnetic field, what will happen? Exciter rotor is turning with the same RPM of the prime mover. So that means there will be a coil set moving inside a magnetic field, which will cause some current to induce, some EMF to induce in the exciter rotor, and it will be an AC supply. As there are three coils, it will be three-phase AC waveform. Then as it connected to the diode rectifier bridge, it will convert this AC supply into a DC supply. Then this DC supply again here apply in the main rotor field. So there will be a north south again. It acts as a permanent magnet. But even though it acts as a permanent magnet, this rotor is rotating with the prime mover. So this north south will be rotating like this. In the same way, it will be rotating in the same speed with the prime mover, which creates a rotating magnetic field. This rotating magnetic field then will act upon the stator winding. There are the copper windings. So this north south rotating and mean the polarity, the field, the magnetic field is varying, cutting the stator winding. It will cause to induce some EMF here. So some voltage will appear. Let's say if the generator is rated to 440 volt to run, from the beginning, depend on the voltage we apply here. Depending the excitation voltage, there will be some voltage. Suppose it's around 400 voltage. And but our requirement is 440 volt. We are using an AVR, automatic voltage regulator, which sends the produced EMF voltage and it will correct the voltage value to the set point. That means to 440. It will increase the excitation voltage, then it will increase the induced EMF of the exciter's rotor, then it will increase in return the main rotor field strength. As per the increased flux density, then the EMF will be increased and corrected to the required rated voltage. Suppose now, as we discussed, now we have EMF here, some voltage appearing here. It is same like that you have pumped your house water tank. Now it's full, but still there will be no water flow if you are not opening any valve, or if you are not utilizing that water to fill a bucket or to have a shower. There will be no water flow in the pipeline. In the same scenario, even though there is a voltage appear in the stator winding output, there will be no current flow unless or otherwise if we switch on the circuit breakers and the contactors, and if only if we are using and if we are consuming this current. So to do that, we have to switch on the circuit breaker. Suppose now we are going to switch on this breaker, make the connection. And the meantime, now we are going to our bus bar is alive, so now we can use these on our particular loads. For easy understanding, I am going to divide the ship's load into three parts: resistive, inductive and capacitive. We will discuss separately in each case how the generator reactions occurs, current flows and magnetism, how the governor will control the active power and the AVR control the reactive power. So in first case, we are going to discuss connecting the resistive load. The resistive loads are here. We can see there are some electronic components with the semiconductors, ceramic components and other things. Even though in reality we cannot find 100% resistive loads, for easy discussion that we are going to assume that there will be a pure resistive load that we are going to connect to the bus bar. So this is the diagram of the pole of the main rotor. Now, as we discussed, as this 440 volt appearing here, there is already a magnetic field rotating inside with the magnitude of 5x. This is there. Once you switch on this main circuit breaker and this contactor and connecting this resistive load, what will happen? As this circuit is completed, then there will be a current flow. I would say it is IR. So okay, I'm going to make it's IR. When there's a current flow, Now what will happen? It clear. Before we discuss, now stator winding is under influence of a rotating magnetic field from the rotor winding. In the same instant, now what is going to happen is there will be a circulating current flowing inside the stator winding. And as we discussed in magnetism theory, when there's a current flowing through a copper coil, there will be an induced magnetism around the coil. So in the same way, as this resistive load is connected and the current starts to flow, there will be an induced magnetic field, a new magnetic field. Let's call it 5R due to this resistive load. And it is found that new magnetic field is in a plane which is 90° perpendicular to the rotating magnetic field of the rotor. Initially here was magnetic field which is rotating. So the new magnetic field which is generated due to this resistive load connected, which is 5R, it is in a different plane, which is 90° different plane from the initial magnetic field, main field. So as these are, suppose this is 5R, this is the magnetic field that the newly developed, and it is 90° out of phase, another plane from the initially generated magnetic field in the rotor. There will be no impact on the magnitude of this initial magnetic field, because it is 90° as the vector that we can see, as it's 90°, no impact on the magnitude of the initial rotor field. So the magnetic field strength is constant. So as far as magnetic field strength is constant, as we know, the EMF here, induced EMF that we discussed, d phi by dt, the magnetic field strength is not changing, so the EMF will not affected. But they have found, due to this new magnetic field, and it is in another plane, there will be a magnetic interaction which will cause the retarding torque on the alternator rotor. So that means it will cause to reduce the speed of the prime mover. So the flux cutting rate will be affected. So the governor is monitoring, sensing the speed of the rotor. As this newly induced magnetic field interact with the magnetic field on the rotor, and it causes the retardant torque, then as the speed drops, the governor will sense that speed drop and increase the amount of fuel to take back the generator speed to normal speed and to restore EMF. In this case, EMF will be reduced due to retarding torque, the flux cutting rate affected. Due to that case, the EMF will be going to lower. So the governor will come to know this before the AVR comes to know, as the speed is dropped initially. So the governor will maintain the fuel to prevent that voltage is dropping down from its rated value. So this is how in resistive load the governor is going to react. So resistive loads we are calling we call it as active loads, because in active loads what we consider is whatever we supplying all the energy, it will convert it into useful energy. Even though there are few losses that we call copper losses, P is equal to I squared R, I mean the current and the resistance. Due to this cable resistance and this, there will be some power dissipation as heat also. Now we are going to discuss when the inductive load is connected to the bus bar, how the magnetism is affected and who is going to take care of that load change and the response done by which component, whether the VR or the governor. To understand that, basically the basic principle behind the RLC circuit we have to discuss. In resistive loads, that we can say the voltage and current is always in phase. You can see it, they both of these lines are in same phase. In inductive load, always current will lag 90 degree from the voltage. In capacitive, the current will lead the voltage by 90 degree. So what we have to understand is, in resistive load, voltage and the current is in the same phase, but in inductive load the current is always lagging 90 degree the voltage, and capacitive load the current is leading 90 degree of the voltage. So now we going to discuss our system. Suppose now we are going to connect this breaker. So now we have just connected the inductive load. Suppose it's a bow thruster motor, water pump motor, any other inductive load. Now what will happen? Due to this connection, there will be a current flow. I will mention it as IL. So this current flow will circulating in this circuit, including the stator winding. Now, as the same before, there will be a new current flow through the stator winding, which is equal to IL, and due to this current flow, as this is a copper conductor and it is subjected to a current flow, there should be induced magnetic field, which we call as phi L. Just before I explained, in inductive circuits the current is lagging 90 degree with compared to the voltage, and also in that case the resistive loads the current and voltage are in same phase, but here in the inductive load the current is lagging. So this current flowing is 90 degree lagging the previous current which flows in the stator winding due to resistive load. So that means this new flux, a new magnetic field generated, it is parallel. It will be parallel and opposed to the initial flux. That is 5L. This one is parallel but in opposite direction. Now as a vector we can see now they are in the same plane, same direction. So this newly generated flux, as it in opposite direction, it will cause to reduce the strength of main rotor magnetic field. In return it will cause to reduce induced EMF. Now it's trying to reduce the induced EMF, dropping down. But as they are not in another 90 degree plane or something, the magnetic reaction between these two fields will not cause any retarding torques. It will not affect on the speed of the prime mover. Instead, it will impact on the magnetic field of the main rotor, reducing its strength, causing EMF to reduce. Then before the governor comes to know about the speed reduction or anything, the VR will monitor and it will sense this voltage EMF reduction and it will increase the excitation voltage. Then the exciter field rotor increase its induced EMF, In return, the main field strength again restore back to maintain the voltage, our set voltage. Finally, we are going to discuss connecting of capacitive loads to the bus bar. So we can connect the capacitive load in ships reality that we normal low voltage ships that we will not come across with large number of capacitive loads, only the fluorescent lamp starter or something. But as a principle to discuss the effect uh, coming from the capacitive load, we'll discuss. So due to this capacitive load connection to the bus bar, there will be a current flow IC, and the same way it will flow from the stator winding, and this time another magnetic field will induce, that we call it as phi c, and it will be in a direction which is parallel and in the same direction of the initial magnetic field of the main field, because you can see I've told you that in capacitive circuits current is lead 90 degree of its voltage. In resistive loads current and voltage in the same phase, but in capacitor it will lead. So due to that principle, so it will lead in phasor diagram we can see to the horizontal it will lead 90 degree, so it will be in the same direction, parallel same direction to the initial rotor field, which will cause to increase the magnitude of the initial rotor field. In return it will tend to increase the voltage here. Let's say it's trying to raise the voltage to some value, but it will not affect any making any retard in torque with the magnetic interaction of the rotor field. It will not create any impact on the rotation of the prime mover. It will not give any retarding force on the rotor. But as the magnetic field strength increase, it will tend to increase the EMF. This field monitored by the AVR, it will sense this increment of EMF, so it will decrease the excitation voltage. Then the exciter field rotor induced EMF will be less, then the magnetic field strength of the main rotor will be less, and restoring the voltage into our set value. Okay, here we are at the end of the discussion. As a summary, we can conclude that the governor is responding for active power change reaction variation, and the AVR will be react on the response on reactive power variation in the bus bar. So thank you for watching this video. In next videos we will discuss about paralleling generators, how the load sharing is taking place, what is load and how it feel by the generator, why we need isochronous governors, and why do we need group governors for load sharings, and these contents will be discussed. Thank you.